Hey, howdy. Howdy. Hello. Good afternoon. It's time to get started with the lecture for today. As you should know by now, the first exam is on Monday. So today what we're going to do is we're going to basically explain what you should expect in the exam. And also, I'm going to discuss some of the problems from the homework. Okay, so for the homework today, what I want you to do is to keep the homework. I'm not going to collect the homework. The reason for that is I want you to make corrections in your homework based on our discussion. And I want you to keep the homework because you will not have to get the homework back before the exam if I collect it today. Okay, so I want you to keep the homework, study with the homework, and then be ready for the exam on Monday. Okay, so today you can ask questions about the homework or about any other topic. But before we get to that, I want to finish, or I want to go over this one more time. The last thing we discussed in class was the continuous probability distribution. So last time we reviewed the discrete probability distributions, and then we also covered the continuous probability distribution. So in terms of the probability density function, which corresponds to the distributions for random variables that are continuous, we know that in order to be a probability density function, it needs to satisfy these three conditions. In some of the problems from the homework, we're asking you to show that the density function that was provided was a probability density function. So in those cases, what you need to do is verify that when you substitute the value of x in the function for the range, which is defined here by r, you get a value that is greater or equal to 0. The second thing that you need to do is to integrate for the limits of the density function and find out if the probability is equal to 1. If you do those two steps, then you can show that the probability density function or the actual function is a probability density function. This part here shows you how to compute the probability for a given interval. Any questions?
Did we have any for homework that were continuous or were they discrete?
You actually have some of them that were continuous. Yeah, the ones that were listed at the end. Yes. So you get that's the homework? Yeah. You need to keep that. Yeah. So again, you will keep the homework because we're gonna discuss the problems today, and you need to have your homework to study for the exam. Okay. Any other questions? Okay, so we discussed a couple of examples, and today I want to work on one more example before we go to the review. So in this problem, this is what we have. We have that the diameter of a particle of contamination in micrometers is modeled by the probability density function f of x equals 2 over x cubed. And that's for x greater than 1. And I want you to find the following probability. The probability of x less than 2, and so on. So let's work on that problem. So this is a probability density function. So this corresponds to a continuous random variable. So if you want to find the probability that x is less than 2, what do? You need to integrate, right? What are the limits for the integral? Why is 1? Because the problem is telling you that x is greater than 1. Okay, so that's your lower bound. And the function is 2 over x cubed dx. So if you solve this, let me do the integral really quick. You have 2x to the minus 3 dx, and these become 2x minus 2 divided by minus 2, evaluated from 1 to 2. So this is equals to 0.75. You have a density function, probability density function. You want to find the probability of x is less than x is less than 2. So you integrate from 1 to 2. Okay, let me show you with a graph. Maybe this will make more sense. So if you compute that probability, this is basically what you're doing. So let's say this is the graph for this probability density function. And you know it goes from 1 up to infinity. So that's the area under the curve, right? And the integral basically, what you do is you look at that area, but you integrate. Now, when you look at the probability of x being less than 2, what you're doing is the following. You're focusing or basically looking at this area. So you integrate from 1 to 2, and that's 0.75. Does that make more sense? Okay, so the density function is basically a curve. It's defined by a function of x. It gives you that curve, and you find the probability you're looking at a specific area of the curve. Let's look at part B. So P for x greater than 5. So here you will come, you will find 5, and you're going to look at this area. Right? So when you define your integral, you have from 5 up to infinity. Correct. 2x over 3 dx. So that is equal to 0.04. You want me to solve the integral? It's the same thing we did for the first one. So you have to evaluate from 5 to infinity. You want me to solve? Yeah, okay. So let me this laser. So you will have 2x minus 2 divided by minus 2, evaluated from 5 to infinite, and this is equal to 2 over x squared. This should be 1 minus 1 over x2. And then when you solve this, this is 0 minus 1 over 25. And this is 0.04. Oh, 0.04. So when you put infinite under 1, that becomes 0. So that's this 0. And then minus, because this is minus 5 squared, 1 over 25. Yeah. Any questions? Okay. part C, probability of x being within 4 and 8. So you integrate from 4 to 8, 2 over x cubed dx, and that is equal to 0.0469. How about the last one? What did you do there? You can do that. That's one way of solving it. There's another way that might be more easier. So when you look at this, you have 4 and 8. So you're looking for this area and this area, right? So one way you can do is to find this and this. The other thing that you can do is to find this one and then 1 minus that, which is the complement. Yes, sir.
You know, when you construct the question that says like this, regarding the function, but if you give us the function, or that.
The function is there.
I know, but if you think that we were like, I just like this stuff.
Okay. So you have this, right? Do you know this area or this probability? What is this, right? So the only thing that you have to do there is 1 minus p so that is equal 1 minus 0.0469. Yeah, this is not the actual representation. As you can see, there's 2 different curves. I'm just drawing that for visual purposes, but that doesn't mean that this is the right distribution. As you said, this area is larger than these two, and this is basically representing this, which is very small. But this is not the right side of the curve. It's just for visual representation. Yes, sir.
It doesn't really have to do with solving the problem, but this x in this case, is that supposed to represent the diameter of the particle?
The diameter of the part?
Question? Is x the size of the particle, or is x the...
Yes, it represents the diameter. Yes.
Doesn't say.
Yeah. Any other questions? Okay. So for the next problem, I want you to work in groups of 2 or 3. And what you're going to do, you're going to turn in this. And if you got the answers right, I'm going to give you a point for the exam. Okay? So this is this. I don't know. So this is a 1 point if you got all the answers right.
I have my
So let's
Oh, really?
see. X is greater than 40.
So,
It's gonna be the. After some, the last two years.
feedback is less than 1.8.
Yeah.
So we're gonna have to do the first and second. So. So it's gonna go from the first one, from 1.8 to -2, and then we gotta do it from -2 to negative. So,
And please read the problem. Read the problem. Make sure that you know what you're doing.
Right down.
Once you got that, it's 45. And this gives us value of 28.
There's a big difference between this problem and the problem we worked in class a few minutes ago.
Yes.
So it's not a density function, it's a cumulative distribution.
So.
No questions asked. Yeah. I will not answer questions. So let me give you a hint. So remember for the discrete distributions, we had the histogram for the probability mass function, right? And then from there, we can create a cumulative distribution, right? So basically, it's the same idea. When you have a density function, you are creating a cumulative distribution for the problem. So what you have in this problem is not this, is this. And this is 1.
I guess
So I'll give you 2 more minutes.
So you got all from the part A, we're getting some. So if we take the integral from negative 2 to 1.8, your value is less than 1.8. You get the integral of 1 x plus 1 dx. That's equal to 1/8 x squared plus 1 x.
The only thing that I can tell you is this is not identical. You don't need to integrate.
Oh, okay.
Okay, so one more hint. You don't need to integrate. this problem. Okay, so time's up. So you can pass your answers to this side of the basket, please. Papers. Okay. Any other papers? Thank you. Okay, so let's discuss this problem. And I think the best about this exercise is that it's going to make you realize the difference between a cumulative and a density function. Okay, so let's refer back to our definition for a cumulative distribution. And one of the things that I noticed and saw several of the answer sheets that show a probability higher than 1. If you get a probability higher than 1, you're doing something wrong. Okay, probabilities are never higher than 1. So that's one thing that you can use for verification. Okay, if you get a probability higher than 1, there's something wrong. Okay, so cumulative distribution function. F of x is of a continuous random variable x with density function. F of x is the integral of ft dt, or f of x, right? So basically what I'm telling you is, if you do the integral, that's f of x. The actual area, or the probability, or the area of the curve, that's the cumulative distribution of your probability density function. So when you create the integral, when you solve the integral, you're getting the cumulative probability up to that point. Okay, so basically, when you go here, let's see. Okay, so knowing that, any idea how to solve part A?
Try to plot it, we didn't have that time. Yeah, we were just plotting by value.
Yes, that's the only thing you have to do. You have to plot the value, because this is your density function, right? The cumulative, what he's saying is, this is always 1. So if you find, let's say this is 1, and this is 2, the cumulative will tell you 0. At this point, this is your probability. At this point, That's probability of 3. So you are accumulating the probabilities and plotting them, or basically constructing your cumulative distribution by adding the probabilities up to the end of the range. So when you come here, probability of x being less than 1.8, you know that f of x is giving you the cumulative distribution. So for 1.8, what's the range that you will use? This one, because 1.8 is between -2 and 2. So you have 0.25 times 1.8 plus 0.5. And that is 0.95. So for part B, you have this. What do you do?
I'll go from -1.5 to 2, it should be 1.
Yeah, you can do that, but since you have the cumulative, it's just easier to look at the complement.
Yeah.
So 1 minus the probability of x being less than or equal to minus 1.5. So in that case, we have 1 minus 0.25 times minus 1.5 plus 0.5. And that equals 0.875. Part C. Yes. And why 0?
X less than -2.
Exactly. So it's given by the actual function. And the last one, so what you do there is you look at the difference between f of 1 and f of -1. Okay, so you're actually looking at the range, right? So f of 1 that should be equal to 0.25 times 1 plus 0.5 minus 0.25 times minus 1 plus 0.5, and that is equal to 0.5. Okay, so if I give you the density function for a continuous random variable, and I ask you for the probability, what do you do? Give you the density function. You integrate, right? If I give you the cumulative, there's no need for integration because you already have the values for the cumulative distribution. You just have to plug in those numbers. Okay, so this is basically the last problem we're discussing. Any questions? Okay, what was that? Redo this? Oh, no. No, there's no redo. So let's move now to the review for the exam. Okay, so the exam will cover up to here, up to this material, continuous random variables, and continuous probability distributions. So for the review, what I did was I create a